Now, let's say something about the dimensionality. So for degrees of freedom, such as spin, the dimensionality of the vector space from which we obtain our state vector is finite dimensional, right? So for example, in the case of spin half, the vector space is obviously two-dimensional. So we can introduce two basis vectors. This is called the spin up vector, and this is given by 1, 0. And the spin down vector, which is given by 0, 1. And then we see that these vectors are eigenvectors of Sz, because when you apply Sz on spin up, you get h bar by 2 spin up, and you apply Sz on spin down, you get minus h bar by 2 spin down. So any arbitrary vector, psi in this vector space, which I'm right now calling C2, can be expressed as a linear combination of the spin up vector and the spin down vector.
Sir, I didn't get the statement you wrote.
This one?
Yes, sir.
So, okay. Remember that when I wrote, I said that the state of the spin degree of freedom of a spin half particle is given by a vector which has this form, right?
Yes, sir.
And psi 1 and psi 2, they were complex numbers. So, how many entries are there in this column matrix? 2, right? So that means that this thing, object, is an element from C2. Right? What is C2? C2 is C1
Complex
cross
space.
C1. Sorry?
C2 is the complex space. Two-dimensional, right?
Two copies of complex numbers, yeah.
Oh, so four-dimensional.
So yeah, here I am. My vector space is over the complex numbers, and because the linear combination coefficients here, these are complex numbers, right? Because these are complex numbers, we only need two vectors to express any vector in C2. And because we can choose these to be complex numbers, we are not restricting ourselves to real numbers. There are two linearly independent basis vectors. And therefore, the dimensionality of this space is 2. Okay, so we are talking about the complex dimensionality. Okay. So it's a vector space over the complex numbers, not the reals. Okay, any more questions? Okay, so it should be kind of obvious that any vector in this space can be expressed as this linear combination. So these coefficients, C up and C down, they are complex in general. And they actually have physical significance. Okay, so what is the physical significance? So the physical significance is this: if the system is in state, say psi, so the ket psi, and we make an observation of S of Z, then the probability that the result of that observation is plus h bar 2 is C up mod squared. Okay, so let's look at this. So if I make an observation of SZ, then the probability that the state that the system will be found with spin up is given by this number's modulus squared. And if on the other hand, the result is the probability, that the result is minus h bar 2 is going to be given by C. Okay. So, given.
So basically it's saying that the coefficient the vectors have, that's the probability of seeing the result upon observation.
The coefficient, yes, almost. The coefficients that the vector has in the basis is the amplitude. C up and C down are known as amplitude. The mod squared of the amplitude gives me the relative probability, okay? So this is known as amplitude. The fact that this quantum mechanics employs complex numbers in this way is of fundamental importance. We don't know why quantum mechanics employs complex numbers. Nobody has been able to formulate a complete description of quantum mechanics excluding complex numbers. And but complex numbers, so the probability and the amplitudes are related, but they are not the same thing. Okay, so this leads to all kinds of interesting stuff such as superposition, interference, which we don't have in classical physics in the same way.
This C up square and C down square, this is what's called Born's rule, right?
This is known as Born rule, yes. That was my next.
I actually looked into it a while ago, and
Yeah.
I think what I found is that people still don't have an explanation for why Born's rule works.
Yeah, no, this is one of the axioms of quantum mechanics. We don't know. This is one of the axioms. Like, it didn't have to be like this. That power could have been fractional. Like, nature could have chosen this to be pi. But that's not what happened. We don't know. Nobody's been able to explain why that square is there. But sorry, Saif, you had more to say?
No. I was just thinking that like Bourne just got lucky with his guess, right? Like he made educated guesses to like what it was, and then he got it.
Yeah, not only that, the famous paper in which Bourne, proposed the Bourne rule. The Bourne rule was proposed in a footnote in that paper. Okay. So yeah, physics is weird. Yeah, Bourne was like, oh, he just threw that away, threw that in as a footnote. All right, so let's say a few more things about this. So if we denote by bra of psi the Hermitian conjugate of psi of ket of psi, which means we take psi, the ket, and we take its transpose and complex conjugate it, then it's easy to see that C up is given by this, and C down is given by this. Okay? And therefore, C up squared is and C down squared.
This is like taking a dot product with a basis vector, right?
Yeah, exactly. That is exactly what it is. Okay? So if, say, psi and phi are two different states or state vectors, then this thing is a linear inner product, okay, which is positive semi-definite. So what does positive semi-definite mean? It means that if you have this thing and you take its inner product with itself, that is either 0 or greater than 0. But if it is 0, it is 0. Let's see. When it's 0, it's if and only if this is the 0, the 0 vector. Okay, so this is 0, 0. Okay. So a vector space with such a positive semi-definite inner product is called a Hilbert space. Okay, and that's named after David Hilbert.
So C up is equal to bra up psi ket. So what does
Right.
this mean?
Oh, this means that's a very good question. So this means that when we have, say, psi and phi, this thing means that we take it's the vector in our product. So this is a column vector, and this is a row vector. So this thing is a vector. This is a matrix multiplication. So the matrix multiplication of a column vector and a row vector will give you a number, right?
So the column is the column vector of infinite dimension. as you said
Here
earlier.
we are dealing with a finite dimension. I will come to the infinite dimension in a moment.
And about the row vector, how
Yeah.
does that work in this situation? What is the
Here, if I give you a column vector, say psi cat, then you find the Hermitian conjugate of that by doing this. You take this and you transpose it, and then you take the complex conjugate, and that is what I called psi dagger, and that gives you this thing. Okay.
Yes, sir, got it.
Okay. Good. Very good. Thank you. Okay, so this is called a Hilbert space.